Imagine you are filling a glass with water at a steady pour. Without a clock, without a ruler, you can often sense when the glass is about to overflow. Your mind is tracking how fast the level rises and how much room is left. That quiet prediction is not magic. It is accumulation. You are adding tiny amounts of water over time until a total appears. Integral calculus is the formal language of that idea, adding many small pieces to recover a whole. Today we build the integral from pictures you already trust. Area as a stack of lines, the triangle formula as a sum of growing slices, curves as messy stacks that still have a total, the elongated S in a textbook as a sum, not a threat, and the deep link between rate and total, which is the heart of the fundamental theorem of calculus. No stage magic, only geometry that becomes arithmetic when the slices get thin. Start with area because area is honest. Take a rectangle that is 4 units wide and 3 units tall. You already know the area is 12, but notice what the product is really doing. It is saying take a vertical strip of height 3 and sweep it across a width of 4. One strip has almost no thickness. Many strips stacked sideways fill the rectangle. Area is length accumulated across another length. 2 dimensions grown from 1. Now replace the rectangle with a triangle. Same base, same height. The school formula says 1/2 base times height. Where does the 1/2 come from? Look at the triangle as a stack of horizontal slices from tip to base. Near the tip the slices are short. Near the base the slices are long. If the sides are straight, those lengths grow at a steady rate. When you add a sequence that grows linearly from 0 to the full base, the average slice length is half the longest slice. Average times height gives the area. The 1/2 is not a superstition. It is the average height of a straight ramp from 0 to full. Make the slices thick and you see a staircase. Gaps and overlaps mock the true edge. Make the slices thinner and the staircase hugs the slope. In the limit, when each slice width is as small as you please, the jagged error vanishes and the sum becomes the true area. That limit of sums is the integral. The elongated S stands for sum. The little dx at the end marks the vanishing width of each strip. Spoken carefully, you are saying add up height times a tiny step in x. Now draw a curve above the axis, any reasonable curve you like. Under the curve, from left endpoint A to right endpoint B, lives a region. That region is again a stack of vertical strips. Strip number I sits at some x, has height equal to the function value there, and has width a tiny step. The integral from A to B of the function is the limit of the sum of those strip areas. If the function is positive, the integral is ordinary geometric area. If the function dips below the axis, strips below count as negative area. The integral is a signed accumulation of height across x. Riemann's picture is exactly that. Choose sample points, build rectangles, add them up, refine the partition. Different choices of sample height give different temporary totals, but for nice functions they all race toward the same number as the mesh of the partition goes to 0. That number is the definite integral. You do not need infinite patience to compute it by hand every time. You need the definition once, so the later shortcuts mean something. Left endpoints, right endpoints, and midpoints are 3 common sampling habits. For a rising curve, left rectangles tend to undershoot and right rectangles tend to overshoot. Midpoints often sit between them. As the strips shrink, the 3 stories agree. That agreement is the definition earning its keep. It tells you the integral is not a private opinion about how to draw boxes. It is a stable limit. Here is a concrete walk. Suppose the function is a constant 2 between 0 and 5. Every strip has height 2. The sum is 2 times 5, which is 10. The integral is 10. Suppose the function is a line that rises from 0 to 4 across an interval of length 4. That is a triangle of area 1/2 times 4 times 4, which is 8. The integral is 8. Suppose the function is a parabola that opens upward. Strips near the middle are taller if the vertex sits there, or shorter if the parabola sits the other way. You can still approximate with many rectangles. Calculus will later hand you an exact antiderivative, but the meaning remains strip sum. Why do people care? Because almost every total in science is an accumulation. Distance is the accumulation of speed over time. Work is the accumulation of force along a path. Charge is the accumulation of current over time. Mass can be the accumulation of density along a rod. Probability over an interval can be the accumulation of a density function. The integral is the universal machine that turns a local rate or density into a global total. That is why the fundamental theorem of calculus feels like a superpower. It says that if a quantity changes with a known rate, the net change of the quantity between two times is the integral of the rate. In symbols you may have seen, the integral of f prime from a to b equals f of b minus f of a. Read it in words. The total of all the tiny changes is the big change. Differentiation splits a total into a rate. Integration gathers a rate back into a total. They are inverse crafts. Picture a car. The speedometer shows rate. The odometer shows total distance. If you could record speed every fraction of a second and sum speed times tiny time, you would rebuild how far the car traveled. That sum is an integral of velocity. If instead you only know the odometer at the start and at the end, the difference already is the integral of velocity, without drawing a single rectangle by hand. The fundamental theorem is the license to swap hard sums for careful antiderivatives when the functions allow it. Antiderivatives are reverse derivatives. If the derivative of x squared is 2x, then an antiderivative of 2x is x squared plus a constant. The constant floats because derivatives kill constants. For a definite integral between two ends, the constant cancels when you subtract. So you evaluate an antiderivative at the right end, subtract the value at the left end, and you have accounted for every strip in between, provided the function is continuous on the interval. That is the practical engine of calculus courses. Meaning still sits in the strips. There is a second phase of the fundamental theorem that students meet later. Define a running area function by integrating from a fixed startup to a moving end x. Then the derivative of that running total, with respect to x, is exactly the original height function at x in words. The edge strip you add when you widen the interval a little is the new contribution. Differentiation recovers the integrand from the accumulated area. Integration and differentiation keep trading places, each undoing the other when the hypotheses hold. Average value is another friendly face of the same idea. The average value of a function on an interval is the integral of the function divided by the length of the interval. Geometrically, it is the height of a rectangle that has the same area as the region under the curve. The triangle story returns. Average height times width equals area. Integration finds the area. Division by width finds the average height. Statistics, physics, and engineering lean on that move constantly. But about volume, spin a region around an axis and you generate a solid. One classic method slices the solid into thin disks or washers. Each disk has a tiny thickness and a face area that depends on the radius at that station. Sum the disk volumes and you have the solid's volume. Another method uses cylindrical shells. Different slicing, same integral philosophy. Accumulation of thin pieces. The universe of multivariable calculus is mostly higher dimensional versions of this habit. A washer is a disk with a hole. You subtract the inner radius contribution from the outer one, still at each station along the axis, still times a tiny thickness. A shell is a thin cylindrical wall. Its volume is roughly circumference times height times thickness. Whether you prefer disks or shells is a question of which radius is easier to write. The philosophy does not change. Thin pieces, honest sum, limit. Arc length and surface area join the same family. A small piece of a smooth curve is almost a straight segment. Its length is roughly the hypotenuse of rise and run. Sum those tiny hypotenuses, and you approach the true length of the graph. Surface area of a surface of revolution is like painting the solid with tiny bands. Again, a local size times a tiny step, added up. Once you see the pattern, new formulas stop feeling like random spells. Limits of integration matter. From a to b means travel along the axis from a toward b, swap the ends, and you flip the sign of the integral. Split an interval at a point c, and the integral from a to b is the sum of the integral from a to c and from c to b when everything is well behaved. Constants factor out of integrals. Sums of functions integrate term by term. These algebraic rules are bookkeeping for strip sums, not separate mysteries. People fear the notation. The elongated s looks ceremonial. The dx looks like a stray letter. Read a definite integral out loud as the signed area or the accumulated total of this density from here to there, taken in tiny steps of the variable. Read an indefinite integral as a family of antiderivatives. The ceremony collapses into a task. Find a total from a rate, or an area from a height function, or a mass from a density. Approximation never really leaves. Even when you have a closed form, computers often integrate by refined Riemann sums, or smarter cousins like trapezoids and Simpson rules or Gaussian quadrature. The definition is not only philosophy, it is an algorithm. When a curve has no elementary antiderivative, the strip sum, done carefully, still answers. Calculus remains geometric even when algebra runs out of closed forms. A short workshop with numbers, the way we did with foreshortening in geometry. True height function equal to 3, interval length equal to 4. Integral equals 12. True height a ramp from 0 to 6 over length 6. Integral equals 1/2 times 6 times 6, which is 18. True height 2, then a jump to 5 on 2 equal halves of an interval of length 4. Integral equals 2 times 2 plus 5 times 2, which is 14. Piecewise stories still add. The integral does not require the world to be one smooth formula. It requires that you can add the pieces you can describe. Try one more by hand in your head. Height equals 1 plus x on the interval from 0 to 2. The graph is a trapezoid with heights 1 and 3. Average height is 2. Width is 2. Area is 4. Or use an antiderivative, x plus 1/2 x squared, evaluate from 0 to 2, and you get the same 4. 2 roads, 1 total. That is the comfort the fundamental theorem is supposed to give. Common mistakes deserve names so you can dodge them. Integrating a rate without matching units yields nonsense. Forgetting that area below the axis subtracts will misread net displacement as total distance. Total distance needs the integral of absolute velocity or careful splits at turning points. Swapping limits without a sign change breaks orientation. Treating every integral as just the antiderivative formula without checking continuity on the interval invites false confidence at corners and jumps. Meaning first, method second. Return to the glass of water. A straight glass is like a constant cross-section. Level rises steadily for a steady pour. A wide bowl is like a changing cross-section. The same pour raises the level slowly when the surface is broad. Relating poured volume to height is again an integral problem, a cousin of the disk method. Your intuition for overflow is a rough integral solver running on experience. Formal calculus makes the same move with numbers you can audit. In physics, the same glass becomes a tank problem. You know how volume depends on height through cross-sectional area. You know how volume grows with time through a pour rate. Chain those relationships, and you recover how height moves with time. Differentials and integrals pass the baton back and forth. The notation is only a disciplined way to refuse to lose track of what is being added. History is brief but grounding. Ancient geometers found areas and volumes with exhaustion, a cousin of limits. Centuries later, Newton and Leibniz forged a shared language for rates and totals, each with his own notation wars. Riemann made the strip sum precise enough for analysis. The elongated S you meet in school is Leibniz's sum sign refined by generations of care. You inherit a tool that was hard-won so that you can spend your effort on models, not on reinventing addition of slices. Close with a compact creed. An integral is a sum of many small contributions. The contributions can be heights times tiny widths, rates times tiny times, densities times tiny lengths. The definite integral between two ends is a number, a total. The fundamental theorem connects that total to the net change of an antiderivative. Differentiation and integration face opposite directions on the same road. Learn to see strips, and you will never again meet the elongated S as a stranger. The next time a chart shows a curve of power use, or speed, or growth, ask what total lives under that curve between two marks. That question is integral calculus in civilian clothes. Area, accumulation, average, and net change are one family. Mathematics gives the family a precise grammar. With that grammar, you can stack the world back together from its thin slices and trust the total you obtain.